Somewhere inside a research facility in Santa Barbara, a machine the size of a chandelier, cooled to a temperature colder than deep space, did something that should not have been possible. It solved a problem in under 5 minutes. A problem that the fastest supercomputer on Earth, a machine built with billions of dollars, millions of processor cores, and decades of engineering, would need 10 septillion years to solve. Google has developed a new quantum chip called Willow, which significantly reduces errors as it scales up, a major breakthrough in quantum error correction. Willow also performed a computation in under 5 minutes that would take a supercomputer 10 septillion years. Read that number again, 10 septillion. That is a 1 followed by 25 zeros. That number does not just exceed the lifespan of every computer ever built combined, it exceeds the age of the universe itself, several trillion times over. And Willow did in 5 minutes what would take that long. But here's where it gets worse. This was not the headline that should have shaken the world. It was the warning shot. Because 18 months later, Google did something even stranger. Something that quietly rewired the entire conversation about what quantum computers are actually for. To understand why this matters, you have to go back further. Not to 2024 when Willow was unveiled, but to 2019. The year Google first whispered a phrase that physicists had been chasing for decades, quantum supremacy. Back then, Google's earlier chip, Sycamore, ran a calculation that, by Google's own claim, would take a classical supercomputer thousands of years. The claim was controversial. IBM pushed back. Skeptics said the comparison was rigged, that with smarter classical algorithms, a regular computer could catch up. For years, that argument simmered in academic journals while the public moved on, assuming quantum computing was still science fiction wearing a lab coat. What most people are not seeing is that this skepticism was not noise. It was the central, unresolved question of an entire scientific field. Quantum computers can produce strange, complex outputs, but proving that those outputs are actually useful, actually verifiable, actually meaningfully faster in a way no classical machine could ever replicate, that is an entirely different and far harder problem. For 6 years, Google's labs worked on exactly that gap. And in late 2025, they closed it. This is where the real story begins. According to Google's own published research, in October 2025, the company's quantum AI division announced something it called quantum echoes, an algorithm run on the same Willow chip, but doing something fundamentally different from anything that came before. Google today claimed that its Willow quantum chip has achieved quantum advantage over a classic supercomputer by successfully running a quantum algorithm 13,000 times faster than a classical algorithm on the fastest classical supercomputer. 13,000 times, not theoretically, not in simulation. If it pans out, this would be the first time a quantum computer has achieved quantum advantage, meaning the result could be checked, reproduced, and verified by other scientists, closing the loophole that had haunted the field since Sycamore. Think about what that means. For the first time in the history of computing, a machine exploiting the literal laws of quantum mechanics did not just outperform classical computers. It proved it in a way that left no room for argument. The lead researchers behind the project didn't hide their excitement. In their own words, this was, as Google's quantum lead Hartmut Neven and his colleague put it, the first time in history that any quantum computer has successfully run a verifiable algorithm that surpasses the ability of supercomputers. But this is not where the story turns from impressive to unsettling. That happens when you ask the next question. What does this algorithm actually do? Here's where it gets worse. The quantum echoes algorithm doesn't just crunch abstract numbers for the sake of a benchmark. It is, in essence, a new kind of scientific instrument, one that lets researchers peer inside the architecture of molecules with a level of precision no microscope, no sonar, no existing measurement tool has ever achieved. Google described the process almost poetically. Our new technique works like a highly advanced echo. We send a carefully crafted signal into our quantum system, perturb one qubit, then precisely reverse the signal's evolution to listen for the echo that comes back. That echo, amplified by quantum interference, reveals structural information that classical methods simply cannot extract. In Google's own analogy, this is the difference between detecting a shipwreck on a sonar screen as a blurry shape and being able to read the actual nameplate bolted to its hull sitting at the bottom of the ocean. And this is where everything changes, because this is not a parlor trick performed on abstract mathematics for the benefit of physicists. Google partnered with researchers at UC Berkeley and ran the algorithm against real molecules, one with 15 atoms, another with 28, and validated the results against traditional nuclear magnetic resonance imaging, the gold standard tool used in chemistry and medicine for decades. The results on our quantum computer matched those of traditional NMR and revealed information not usually available from NMR, which is a crucial validation of our approach. The quantum computer did not just match the old tool, it exceeded it. It saw things the old tool was structurally incapable of seeing. Sit with that for a moment. A machine that operates on principles most humans cannot intuitively grasp, superposition, entanglement, particles existing in multiple states simultaneously until observed, has just demonstrated it can map molecular structure better than the instruments chemists and drug developers have relied on for half a century. This is not chaos. This is strategy. Years of quiet, deliberate infrastructure building aim precisely at the moment when quantum computing stops being a laboratory curiosity and starts becoming a tool that reshapes industries. But to understand why this is dangerous, not science fiction dangerous, but geopolitically and economically dangerous, you need to understand what actually sits underneath this breakthrough. Because the headline number, the 13,000x speed claim, is not really the story. The real story is what had to be solved just to get a quantum computer stable enough to attempt this in the first place. For nearly 30 years, the single greatest obstacle in quantum computing was not power. It was noise. Qubits, the basic unit of quantum information, are catastrophically fragile. They interact with their environment, lose their quantum state, and introduce errors at a rate that, historically, got worse the bigger you built the machine. Scaling up a quantum computer used to mean scaling up its failure rate. This was the central career-defining problem of an entire generation of physicists, dating back to a 1995 theoretical proposal by Peter Shor on how error correction might even be mathematically possible. Errors are one of the greatest challenges in quantum computing, since qubits, the units of computation in quantum computers, have a tendency to rapidly exchange information with their environment, making it difficult to protect the information needed to complete a computation. What Willow did, before quantum echoes ever ran, was crack that exact problem. Google's engineers built grids of qubits, first 3x3, then 5x5, then 7x7, and watched something that should not happen under classical engineering logic. As the system got bigger, it got more reliable, not less. We tested ever larger arrays of physical qubits, scaling up from a grid of 3x3 encoded qubits to a grid of 5x5 to a grid of 7x7, and each time, using our latest advances in quantum error correction, we were able to cut the error rate in half. In other words, we achieved an exponential reduction in the error rate. In the field, this threshold has a name, below threshold. It is the single most sought-after milestone in the entire discipline, and this has been an outstanding challenge since quantum error correction was introduced by Peter Shor in 1995. This is the part most coverage glossed over, not the speed, the stability, because speed without stability is a magic trick. Stability that scales is an industry. And once you understand that distinction, the next piece of this story stops looking like incremental scientific progress and starts looking like a power transition happening in plain sight. Because here is what most people are not seeing. This was never just a Google story. It is a national power story wearing a corporate logo. Quantum computing sits at the intersection of three of the most consequential domains of 21st century power: medicine, materials science, and cryptography. Two of those are about who gets to cure diseases and build better batteries first. The third is about who gets to read everyone else's secrets. Modern encryption, the cryptographic backbone protecting financial systems, government communications, military command structures, and your own private data, relies on mathematical problems that are functionally impossible for classical computers to solve in a human lifetime. Factoring extremely large numbers, for instance, underpins the security protocol protecting much of the digital world. A sufficiently powerful, sufficiently stable, fault-tolerant quantum computer does not just solve that problem faster. It potentially dissolves the entire premise that this kind of encryption was ever truly secure. This is the silent reason intelligence agencies, defense ministries, and national security analysts in Washington, Beijing, London, and beyond have been tracking Google's quantum publications with far more urgency than the average tech headline suggests. A breakthrough framed by Google as a step toward curing disease and designing better batteries is, from a different vantage point, also a step toward a world where whoever builds the first truly fault-tolerant quantum machine holds a temporary, possibly decisive window in which they could decrypt communications the rest of the world still believes are unreadable. Read that again. Not could read more data. Could potentially unlock data already stolen and stored years ago, waiting for exactly this moment. A strategy intelligence analysts have openly discussed under the term harvest now, decrypt later. Adversarial states, according to widely discussed assessments in the cybersecurity world, have been quietly collecting encrypted data for years, betting that someday a machine like Willow's successor will hand them the key. This is where the corporate press release and the geopolitical brief start to diverge sharply. Google's public framing is optimistic, almost utopian. Drug discovery, material science, better batteries, a quantum scope for nature itself. Quantum computing-enhanced NMR could become a powerful tool in drug discovery, helping determine how potential medicines bind to their targets, or in materials science for characterizing the molecular structure of new materials like polymers, battery components, or even the materials that comprise our quantum bits. All of that is true. None of it is the whole picture. Because the same instrument that maps a molecule's hidden architecture is, underneath the hood, demonstrating a class of computational power that has only one historical parallel. The moment a handful of nations realized that splitting an atom could either power a city or erase one. Quantum computing does not have a single dramatic Hiroshima moment to anchor public fear the way nuclear physics did. Its danger is quieter, slower, and in some ways more disorienting, because it does not destroy cities, it destroys assumptions. Assumptions about privacy, assumptions about financial security, assumptions about which nations and which companies hold leverage over global infrastructure a decade from now. And the escalation is not slowing down, it is accelerating, and accelerating in a direction few outside the field anticipated. In March of 2026, Google's Quantum Lab made a move that, on the surface, looked like a footnote, but inside the industry was treated as a strategic signal. After more than a decade of betting almost exclusively on superconducting qubits, the technology underpinning both Sycamore and Willow, Google added an entirely second hardware approach to its roadmap: neutral atom qubits. In March 2026, the lab widened its bet by adding neutral atom hardware as a second modality, positioning itself to scale in both circuit depth and qubit count. Why does that matter? Because a company does not diversify its core technological bet unless it believes the race is far from over, and unless it suspects that a single architecture might not be enough to win it. Superconducting qubits, the kind inside Willow, require dilution refrigerators colder than outer space and offer extremely fast operations, but they're notoriously difficult to scale into the millions of qubits that true fault-tolerant computing will eventually require. Neutral atom systems offer a different set of trade-offs: potentially easier scaling, different error profiles, different physical limitations. By placing chips on two separate technological horses simultaneously, Google effectively signaled to every competitor, every government, and every investor watching this field: we are not optimizing for the next headline, we are optimizing for the next decade. And this is where the power shift becomes undeniable. Because Google is not racing against silence, it is racing against IBM, against Chinese state-backed quantum programs, against a growing constellation of well-funded startups, and against entire national governments treating quantum computing as a strategic asset on par with semiconductor manufacturing. Alphabet's Quantum Lab built the chips behind two of the field's most famous milestones: the 2019 Beyond classical result and the Willow error correction breakthrough. But famous does not mean uncontested. Behind closed doors, this is one of the most fiercely competitive technological arenas on the planet, with national governments, not just corporations, pouring billions into the chase. France alone, for instance, has committed over €1 billion in additional public funding toward its national quantum strategy, a signal that this is no longer viewed as a private sector science experiment, but as sovereign infrastructure. Here's where the human dimension of this story sharpens into focus. Behind every line of this research sits a name, and one of those names recently received the highest possible validation science can offer. The foundational physics behind superconducting qubits, the macroscopic quantum effect first observed back in 1985, earned its discoverers the ultimate recognition 4 decades later. This field of research began with the groundbreaking discovery of the macroscopic quantum effect in 1985, an achievement that earned John Clark, Michel Devore, and John Martinez the status of 2025 physics Nobel laureates. Read that again. The physics that makes Willow possible was not some recent corporate invention dreamed up in a Silicon Valley sprint. It was decades of patient, fundamental science, only now converging with industrial-scale engineering muscle and venture capital urgency. That convergence is precisely what makes this moment different from every quantum hype cycle that came before it. For years, skeptics dismissed quantum computing as perpetually 5 years away from anything useful, a punchline among hardware engineers, a fundraising buzzword among startups. What changed is not the marketing, it's the verification. Across its entire 105-qubit array, it features fidelities of 99.97% for single-qubit gates, 99.88% for entangling gates, and 99.5% for readout. These are not soft, aspirational numbers. These are hard engineering benchmarks, independently scrutinizable, published in peer-reviewed journals. But, and this is the part that should genuinely unsettle you, Google itself is telling you this is still just the beginning. Internally, the company has mapped out what it calls a roadmap of 6 milestones toward a fully fault-tolerant quantum computer, the kind of machine that could run algorithms of unlimited complexity without being throttled by error accumulation. Willow and Quantum Echoes represent progress toward roughly the third of those 6 milestones. As we march toward our next milestone, a long-lived logical qubit, we are fully aware of the numerous challenges ahead. And according to the lab's own founder, the truly transformative machine, the one capable of reshaping industries at scale, isn't expected to arrive tomorrow or even in the next 2 or 3 years. By his own account, the largest milestone machine on Google's roadmap is projected to appear somewhere around the end of this decade. Think about what that timeline actually means. We are not talking about quantum computing as a distant theoretical possibility anymore. We are talking about a 4-year countdown to an inflection point that intelligence agencies, pharmaceutical giants, material scientists, and cryptographers are already quietly preparing for, some by accelerating their own quantum programs, others by racing to deploy post-quantum encryption standards designed to resist exactly the kind of machine Google is building, and this is where the consequences stop being abstract. Governments around the world are already moving. The U.S. National Institute of Standards and Technology has spent years developing and standardizing new cryptographic algorithms specifically engineered to resist quantum attacks, a tacit admission from the heart of the American security establishment that current encryption has an expiration date, even if nobody can say the exact year it arrives. Financial institutions are quietly auditing which of their systems rely on cryptography vulnerable to a future quantum break. Defense agencies in multiple countries have begun migrating sensitive long-term data to quantum-resistant protocols, not because the threat is imminent today, but because data stolen today could be unlocked a decade from now. And some secrets are still dangerous a decade later. This is the strange asymmetry at the heart of the quantum era. The breakthrough does not need to be finished to be dangerous. It only needs to be plausible enough and close enough on the horizon to force every major institution on Earth to begin hedging against a future none of them can fully predict. And the competition shows no sign of slowing. Just days before this very research circulated, China's National Supercomputing Center introduced a new supercomputer of its own, a reminder that classical computing power is not standing still while quantum computing accelerates. The two races are running in parallel, each side hedging its bets, each side aware that whoever falls decisively behind in either domain inherits a strategic vulnerability that compounds for decades. Multiple companies, Honeywell's Quantinuum, a constellation of well-funded startups, research consortiums spanning Europe and Asia, are all racing toward variations of the same prize, using different physical architectures, different bets on which quantum technology will ultimately scale. What most people watching this story from the outside fail to grasp is that there will likely not be one singular, cinematic, we broke physics moment announced on a stage with applause and confetti. This is not how this kind of power transition tends to unfold. It unfolds the way Willow did, in increments, in dense academic papers, in benchmark numbers that read like science fiction to outsiders and like sober engineering milestones to the people building them. It unfolds in quiet additions to a hardware roadmap, like the March 2026 neutral atom pivot that barely make a ripple in mainstream coverage, but send a clear signal to anyone paying close attention. The race is not over, and no single architecture has yet secured permanent victory. But here's the part that should stay with you long after this video ends. Quantum Echoes was, by Google's own description, a proof of principle, a controlled demonstration on small molecules, validated against existing tools, designed to prove the method works before scaling it toward problems too complex for any existing instrument to verify at all. In a proof of principle experiment in partnership with the University of California, Berkeley, we ran the Quantum Echoes algorithm on our Willow chip to study two molecules, one with 15 atoms and another with 28 atoms, to verify this approach. 15 atoms, 28 atoms. That is almost laughably small compared to the molecular complexity of, say, a novel cancer drug, a next-generation battery electrolyte, or a synthetic material engineered at the atomic scale to do something nature never designed. The machine that just outpaced the world's fastest supercomputer by 13,000 times was tested on structures simple enough to double-check against an MRI machine. So ask yourself the question nobody in the press conferences is asking out loud. What happens when the same approach is pointed not at a 28-atom molecule that can be cross-checked against existing tools, but at a problem so complex that no classical method exists to verify the answer at all? At that point, we are not just talking about faster computation. We are talking about a tool that produces answers nobody can independently confirm. Answers we may simply have to trust, because no other instrument on Earth is capable of checking the machine's work. That is not a hypothetical engineering challenge. That is an epistemological one. It is the difference between a faster calculator and an oracle. And the line between those two things is exactly where this technology is currently heading on a publicly stated timeline funded by some of the most powerful institutions and governments on the planet. Google calls Willow a step toward commercially relevant applications. This achievement marks a significant step towards building commercially relevant quantum computers that can revolutionize fields like medicine, energy, and AI. That framing is not false, but it is incomplete in the way that matters most. Because every technology described as commercially relevant in human history, from the printing press to nuclear fission to the internet itself, has also eventually become a strategic asset that nations fight to control, restrict, weaponize, or monopolize. There is no version of quantum computing's future where that pattern simply does not apply. So here's where this leaves us, standing at the edge of a technology most of the public still associates with science fiction, while inside research labs in Santa Barbara, Beijing, London, and a dozen other cities, teams of physicists are quietly, methodically checking items off a 6-milestone roadmap toward a machine none of us can fully imagine the consequences of yet. The chip exists, the error correction works, the algorithm has been verified, the Nobel Committee has already validated the underlying physics. The roadmap has a stated endpoint somewhere near the end of this decade. Every major government on Earth is already hedging against the moment this technology matures, even as the public conversation remains fixated on chatbots and consumer AI. What we don't know, what nobody currently knows, not Google, not its competitors, not the intelligence agencies tracking this race, is which laboratory crosses that final threshold first, what they choose to do with that capability in the narrow window before everyone else catches up, and whether the world's cryptographic, financial, and security infrastructure will actually be ready in time, or whether we are quietly building toward a moment of exposure nobody fully understands until it has already happened. Willow didn't break physics. It obeyed it more precisely than any machine humans have ever built. But in doing so, it may have started a countdown that very few people outside a handful of laboratories are actually watching. The only question left is simple, and nobody, not Google, not its rivals, not a single government on Earth, has a verified answer yet. When that countdown reaches 0, who gets there first?